Trigonomic equations. So today we're going to solve a little bit more complex trigonomic equations, both in radians and degrees with restricted domains, and then we're also going to talk about a general solution today. So solve the following trigonomic equations algebraically using exact values. Okay, so to solve any kind of trigonomic equation, as long as it's linear, what you want to do is you want to isolate the trig ratio. So we're going to isolate cos of theta by moving the -1 and the 2 to the other side of the equation. So move 1 over becomes a +1, divide by 2, cos of theta is equal to 1/2. So what I'm looking for is I'm looking for the values of theta within this domain from 0 to 2 pi, so that tells me my solution should be in a radian. And we're looking for all the solutions of theta when cos of theta gives a positive ratio of 1/2. So as you recall on our unit circles, our x-coordinate on our unit circle is our cosine ratio, our y-coordinate is our sine ratio, and then our tangent ratio is sine over cos. So this was a review from last week. Okay, so what we're going to do is simply look up, we are rotating from 0 to 2 pi, we're simply looking up when cos of theta is equal to 1/2, so we're looking on our unit circle when our x values are equal to a +1/2. So I'm looking at my x-coordinates, which is here, so my first solution should occur at pi/3, and then I'm going to continue to rotate around a full pi, and the other time when cos of theta is equal to 1/2 would be at 5 pi/3. So my solution for this would be pi/3 and 5 pi/3. First question, fairly straightforward. Okay, if we were to talk about a general solution, so a general solution is when the domain isn't actually given and you have to find a solution for all rotations of your angle. So if we talk about a general solution, we want to think about, well, what if this domain wasn't given and we could honestly rotate to this terminal arm over and over and over again. So it's kind of like a coterminal angle in a way. So thinking back to our unit circle, right? This is our terminal arm at pi/3, right? So this is within the domain of 0 to 2 pi. But what if it was 0 to 4 pi? That means I'd have to rotate once, rotate again, right? So I would have to add a full rotation to get back to this solution, right? Or I'd have to add 2 full rotations, or 3 full rotations, or 4 or 5 or 6, and it can continue to go on forever and ever and ever. So when we talk about a general solution, we're talking about rotating around this unit circle indefinitely. We're never going to stop. So we want to give all of the possible solutions for this terminal arm. Okay, same as we want to give all the possible solutions for this terminal arm. These two angles do not relate to each other in a common angle, so we'd have to have 2 separate general solutions. Okay, so how do we write the general solution? We're going to say theta is equal to, we're going to start with our solution on our first terminal arm, and I want to add 2 pi's to this, but how many times do I want to add those 2 pi's? I want to add it n times for the number of rotations we're rotating, and technically we could get to this terminal arm by adding 2 pi's or subtracting. So after we've added 2n pi's or 2 pi n's, we're going to say n belongs to the integers to recognize that we are going to add or subtract 2 pi. And then my other solution would be 5 pi/3, and I'm also going to add full rotations to this. Okay, so this would be my solution within the domain given. This would be our general solution. All right, question number 2. So as we go on, things are going to get a little bit more complex. Okay, so question number 2. So just like solving any algebraic equations, we want to collect our sine of thetas to one side of the equation. So I'm going to bring this 3 sine of theta over here, by subtracting it. At the same time, I'm going to bring this positive 2 over to here by subtracting that. So 5 sine of thetas minus 3 sine of thetas leaves me with 2 sine thetas, and that's going to equal a negative 1. I am then going to divide by 2, and I'm left with sine of theta is equal to negative 1/2. So once again, I am going to go to my unit circle and I am going to find my solutions when sine of theta is equal to a negative 1/2 now in this same domain from 0 to 2 pi. So on my unit circle, I'm looking for when sine of theta, which is now my y values, so now I'm looking at my y values. So here would be my first solution at 7 pi over 6. And my second solution would occur here at 11 pi over 6. So these first couple examples are pretty straightforward. We're just taking those answers from our unit circle and we're solving for that size of the angle from 0 to 2 pi. Now our general solution, again, I want to go back to my unit circle and see if...
Can I get a custodian to the office with a mop, please?
To see if these two angles are related to each other in a common way, and they're not. So I would have to add 2 pi's to my 7 pi over 6 indefinitely to get my general solution. Same with the 11 pi over 6. So my general solution would be 7 pi over 6 plus 2 pi n, where n belongs to the integers, and 11 pi over 6 plus 2 pi n, where n belongs to the integers. All right, moving on. Number 3. 3 cosecant of negative 6 minus 6 is equal to 0. So in this question, again, I'm going to isolate cosecant of x by moving 6 to the other side of my equation. Divide by 3. Oh, and this is a typo, so let's just change this to a theta, not an x. Divide by 3, and I get a value of 2. Well, I don't necessarily want to work in a reciprocal function, so what we're going to do before we actually solve this equation, I'm going to change this to my reciprocal function of cosecant. And my reciprocal function of cosecant is sine of theta, so I'm going to change this to a sine of theta, and I'm going to reciprocate the ratio. So instead of a 2 over 1, it's going to be a 1 over 2. And now, straightforward, we are solving this equation from 0 to 360, so now my solution should be in degrees. We're looking when sine is equal to 1/2, so here at 30 degrees, and then here at 150 degrees. So my solution should be 30 degrees and 150 degrees. And then if we talked about that general solution again, theta is going to equal 30. I'm going to write it a little bit different now because you should recognize both ways it can be written. Rather than n belonging to the integers, instead of adding 2n pi, we can say we could add or subtract. And we don't want to add 2 pi's because we're working in degrees. We're going to add 300 or subtract 360 degree times n. And instead of n belonging to the integers, because I'm adding and subtracting here, n would have to belong to the whole number system. My other solution would be 150 degrees plus or minus 360n, where n belongs to the whole numbers. Okay? All right, so the first 3 were pretty straightforward. Okay, we're now going to move on to quadratic trig functions, or trig equations. So a little trickier, okay? So we now need to incorporate factoring in order to solve the following equations. So you want to give an exact answers where possible, round to the nearest thousandth of a radian or to the nearest degree, depending on If we can give an exact value, we will. If we can't, then we're going to have to round. Okay? All right, so the first equation is sine squared theta minus sine theta equals 0. So what this is a short form of saying sine of theta all squared minus sine of theta. Okay? So how we want to tackle these quadratic trigonomic functions is similar just to a quadratic function. So this would be very similar as asking the equation x squared minus x equals 0. What we'd want to do is we'd want to factor this by factoring out a common factor of x. And sometimes students change this to an x and solve for x first and then just change their x back to a sine of theta, which you can totally do. So here we'd get a value of x equals 0 and x equals 1. Okay? If you factored this in terms of a trig function, I would take out a common factor of sine of theta, and I'm left with sine of theta minus 1. So then I have two solutions for sine of theta. I have sine of theta is equal to 0, and I have sine of theta is equal to 1. So from here we're asked to solve for theta in the domain 0 to 2 pi. So now I have to look up two different ratios on my unit circle to get my solutions. So I'm first going to look up my 0 degree ratio, my ratio of 0. And so remember we're talking about sine of x, which is our x coordinate. So the first solution would be at 0 radians. Okay? So 0 radians, not 0 degrees, because we're working in radians. The second time when sine is 0 would be at pi. And then the third time it would be at 0 would be at 2 pi. So there's actually three solutions for when sine of theta is equal to 0, because I'm working in the domain that is greater than or equal to 0 and less than or equal to 2 pi. So those have to actually be included in my solution. So my solution for this ratio would be 0, pi, and 2 pi. My second solution is when sine of theta is equal to 1. So on my unit circle, there's only one scenario when that occurs, which is at pi over 2. Okay, so these would be all of the solutions for this equation. Well, now I want to talk about the general solution. So our general solution for theta, well, I don't need to include every one of these solutions and add 2 pi to them, because technically these solutions are all differencing by one another by pi. So technically my general solution to get to 0 and 0, the difference between these two terminal arms is actually just every pi, right? So I wouldn't go every 2 pi. In this case, I just have to go every pi. So, and I wouldn't even have to include 0. I just have to say n pi plus, and that's it. I wouldn't even have to add or subtract anything. But then I'd want to say n belongs to my integers. And then my second solution as my general solution would be pi over 2. And then in this case, I would have to add 2 pi n's, where n belongs to the integers. Because to get back to this terminal arm each time, I would have to add a full rotation, which is 2 pi. Okay? All right, so moving on, let's look at question B. Tan squared theta minus 5 tangent of theta plus 4 is equal to 0. So similarly, we want to think of this as like a quadratic equation. So if I were to write this as a quadratic equation similar to this, would be x squared minus 5x plus 4. And so how would you solve this quadratic equation? Well, I'd have to factor it, and the factors of 4 that add together to give me a negative 5 would be x minus 4 and x minus 1, and our solutions would be 4 and 1. So similarly, we want to factor this in the same way. What factors of 4 when added together will give me a negative 5 in the middle? So my factors would be tangent of theta minus 1 and tangent of theta minus 4 equals 0. So my two solutions for tangent of theta would be tan of theta is equal to 1 and tangent of theta is equal to 4. All right, so looking at my unit circle does not have tangents on it, but tangent of theta is equal to 1. I know tan is sine over cos. So to get a value of 1, I'd have to divide the same values. Sine and cos would have to be the same ratio, right? Because anything divided by itself would be 1. So when are sine and cos the same ratio is at this 45-degree mark. Okay? So sine over cos would be, and we're working in terms of radians. We're looking when it's positive 1, which would be in this quadrant. So pi over 4 would be one of my solutions. And then my second solution would be if I'm taking a negative divided by a negative, I'd also end up with a positive 1. So my second solution would be a 5 pi over 4. So my two solutions would be pi over 4 and 5 pi over 4. All right. Now we want to look up when tangent of theta is equal to 4. Well, unfortunately, 4 does not lie on the unit circle. This is not going to work out to a nicely 30, 45, or 60-degree reference angle. So this is where we have to round to the nearest radian in this case. So what I want to do is I want to figure out my reference angle for this value. So I'm going to go to my calculator. I'm going to make sure my mode is on radian mode. I am going to take second tan of 4, and I get a radian of 1.32. Oh, and it says round to the nearest thousand up in our question, so we're going to round to 1.326. So now using this reference angle and the cast rule, we're going to get the solutions for this guy. So I'm going to go back to my tangent ratio. My tangent ratio is positive. So using my cast rule, when is tangent positive? And it's going to occur in quadrant 1, which is 1.326. So one of my solutions for this would be 1.326. And then my other solution is going to occur here. So reference angle, same reference angle, I'd have to add that to pi. So if I just take that previous answer and add it to pi, I get my other solution, 4.467. So these four solutions would represent the solution to this quadratic trigonometric function. All right, what if we wanted to talk about our general solution? Well, if you think about this general solution, let's go back to our first. So we have pi over 4 here and a 5 pi over 4 here. So technically, I don't need to write both of these angles as my solution with adding a full rotation, because if I just add a pi to this angle, I'm going to get this solution. And if I add another pi to this solution, I am going to get back to this terminal arm here. So these angles actually relate to each other by pi radians. So the only solution I need for this first one is pi over 4 plus, I'm going to add not 2 pi, but pi radians each time, where n belongs to the integers. I can also do the same thing for here, because we're working in this quadrant. In this quadrant, really I'm adding a full pi here and a full pi here to go back and forth from my two solutions. So my second solution would be 1.326 plus pi n, where n belongs to the integers. Okay. All right, and then question C. It says sine squared x is equal to, or minus 1 is equal to 0. If you look, this actually does not give a domain value. So when it doesn't give the domain value, then that means all they're asking for is your general solution. Okay, but you still need to find the solutions within one rotation to give that general solution. Okay, and because it doesn't give your domain, then technically it's your choice whether you give your answer in degrees or radians. So let's just, we'll do both. So first thing I want to do is I want to solve for x here. And there's two ways you could solve for x here. You could move 1 over to the other side of the equation and then square both sides to get your solution. So when I take the square root of this, or sorry, not square both sides, but square root, I get plus or minus 1. The other way you could think of this is by factoring a difference of squares, right? So remember, sine squared x is technically the same as like an x squared minus 1. And I could factor this as like an x plus 1 and an x minus 1. So in terms of sine, it'd be sine of theta, sine of x plus 1 and sine of x minus 1. And just recognize we don't always have to use the symbol theta. You could use x's or y's or a's and b's. It doesn't matter. Okay, so we're going to get the same solution as this. Sine of x is equal to plus or minus 1. Okay, so now we're going to look these ratios up on our unit circle. When is sine of x equal to positive or negative 1? So positive 1 here, negative 1 here. In degrees would be 90 or 270. So x would equal 90 degrees or 270. Or if you answer this question in radians, it would be pi over 2 and 3 pi over 2. Okay? So these are not my answers to the question, right? These are just guiding me to get my general solution. Okay, because we don't have a domain, we're specifically just asked for the general solution here. And so when you look at the 90 and 270, these are actually related to each other over time by simply adding a 180 degrees. So again, I don't have to write both of these answers as my general solution. I just need to write the 90 degree mark and continue to add 180 to it. So 90 degrees plus 180 degrees n, where n belongs to the integers, or in radians would be pi over 2 plus pi n, where n belongs to the integers. Okay, so in this case, no domain is given. All we're looking for is this general solution. Okay. All right, I have 2 here to try on your own. Okay, but I still will quickly work through them with you. Okay, so looking at this is a quadratic cosine function. I'm going to factor this. So the factors of negative 2 that add to negative 1 would be cos of theta minus 2 and cos of theta plus 1. So I get solutions of, or ratios of cos of theta is equal to 2 and cos of theta is equal to a negative 1. Well, technically, you cannot have a ratio for cos or sine of theta that is greater than 1. So maybe just make a note of that. A ratio for cosine or sine must always have a value less than 1 or greater than negative 1. Okay, so it has to be basically in between positive 1 and negative 1. Okay, so when I see this, if this value is beyond 1, I'm going to say right away this has no solution. Right, this is definitely not on my unit circle, and even if I try to take the cosine ratio of that, you get an error. Okay, so another way to identify it. Cos of negative 1 on our unit circles is here at 180 degrees. We're working in degrees here, so theta would be 180. Okay, so my only solution for theta here would be 180 degrees. And you're done. That's all. That would be your solution. Okay, you don't have to do the general solution. We were just doing it in the previous examples as practice, but if the domain is given to you, then you just ask for that one solution. Okay, question 2, or B. Here, there is no domain given, so in this case, the general solution is going to be our answer. So if I were to solve this for cos of theta, I'm going to take the square root. Remember, this should be a plus or minus 1. So my solutions for theta here on my unit circle, when cos is positive or a negative 1, would be 0, 180, 360, and so on. So within one rotation would be this, or in radians would be this, 0, pi, and 2 pi. We're not looking for those solutions, we are looking for a general solution here. So my general solution is simply going to be, these all relate to each other by 180 degrees. So it's simply 180 degrees n, where n belongs to the integers, or pi n, where n belongs to the integers. And that is solving quadratic trigonometric equations.